Hi everyone, my name is Viraz and this is my submission for the Eat Build With Hackathon, EIP 7702 Cross-Chain Credit Evaluator. And the idea and the motivation behind this project is multifold. So firstly, I have had the view that on-chain governance systems are not efficient at all and are unfair in a sense that the voting power depends on the total balances of users. Whereas with this use case, the idea is that to assign voting power based on a borrowing position of an asset and generating a credit score. So the voting power is assigned based on that credit score then. And then to again prevent from these Sybil attacks and things like that. And which is again and to design a system that is more fair for everyone, the whales and the fishes, where for example if you have different borrowing positions in Aave, for example. So the idea is that we would have one credit token, and if that particular borrow position is the dominant borrow position out of the others, then you get assigned a certain credit score, and based on that credit score, you get a voting power. So that's the whole idea. Right, and then the second point that I wanted to mention was that as we are seeing, there are different L2s that are being launched and catering to different kinds of use cases, and there are a lot of times there are these scenarios where different DeFi protocols, for example, like major ones, are not on those new L2s and things like that. So the idea is that this is a cross-chain credit evaluator in a sense that the users get assigned a credit score on a source chain where Aave V3 has been deployed. And then on the destination chain, we are considering Bob L2 in this case, which is focusing on the intersection of Ethereum and Bitcoin. Aave V3 hasn't been deployed there. So the idea is that we compute the credit score on the source chain, and then through Chainlink CCIP, we make a cross-chain message, and then on the destination chain we receive that message which contains the credit score, and then the vote and we assume in this use case that we have a Bob governor, which is basically an on-chain governance contract. And so based on the voting power a user has on a source chain, they get assigned a voting power based on the borrow position a user has on the source chain, they get assigned a voting power on the destination chain, which can which can give them a good amount of power in terms of voting on proposals, or like creating proposals and things like that. So yeah, let's dive into it. So there are three major components, like I said. One, of course, is EIP 7702, which has been the talk of the town with after the Petra upgrade. And the idea is that people on the source and the destination chain can do these batch operations very easily with the smart contract code attached to their EOA account. And this project uses Foundry, of course, in terms of like the tests and everything. And then you have trade dedicated borrowing with Aave V3 on the source chain. And thirdly, we have, of course, cross-chain messaging with Chainlink CCIP. So I'll just quickly dive into the architecture as well, where we have, as you can see, we have this credit evaluator on the source chain, and the user uses EIP 7702 to approve and then compute their credit score and things like that. And then you have a CCIP component which is used for making the cross-chain message, and then there's a credit receiver on the destination chain, which is setting the credit score in storage, and then the user can just get assigned voting power, and they can interact with this Bob governor contract and create proposals and also vote on proposals based on their voting power and things like that. And of course, there is a section of relayers as well, where which are monitoring the user's credit score. So for example, if I got assigned a good credit score and I have now a voting power on the destination chain, but after some time I again borrowed some more assets and my credit score sort of went below a certain threshold, so these relayers are basically monitoring that and will be able to trigger a slash, which means that my voting power on the destination chain gets slashed. And so and then I don't have any power on the destination chain in terms of making proposals and voting on proposals, things like that. And again, there is a certain withdrawal delay as well. So in case, for example, if because the idea is that the user locks in their borrowed credit tokens in this contract as an escrow, in terms of acting as a protection mechanism for the whole protocol. And then there's other Sybil preventive measures taken, Sybil attack preventive measures, where the user can only make a withdrawal after a certain delay. So it's not like they can first compute their credit score and then vote on a very impactful proposal on the destination chain and straight away do a withdrawal. So it doesn't work like that. There's a withdrawal delay that's been set during the deployment time, and I'll dive more into that. and after that only they can do a withdrawal. And yeah, and so yeah, let's get started. And there are these steps that you can use to interact with the repository, and of course, like run tests, compile contracts, and things like that. So yeah, let's dive into the smart contracts now. The first one we have is a EIP 7702 delegator. This is a simple multi-call delegator contract where the user can easily execute batch operations, and this uses EC DSA signature verification as well. So user can just sign the batch message, and then a relayer or someone else can sponsor their operation through by paying for gas and then execute it, or the user can also execute it by themselves. So it has both like the signature verification support, or if the user wants to make a direct call, they can do a direct call as well, and it just executes a call operation. So that's it. And then we check for whether the operation was successful or not. So yeah, that's that. And then this is the most important bit, which is the credit evaluator, where the idea is that we evaluate the and compute the credit score, and then send a cross-chain message if that particular credit score is within the certain threshold. And the idea is that there's also a fee involved for the relayers, so it's an incentive for them to make cross-chain calls when like doing slashing, for example. So if I as a relayer I'm able to slash successfully a user, then I get paid a portion of the fee, which is basically the borrowed credit token that's been locked in this contract. So there's more details, of course, in the whole description, and which talks about the flow. But the idea is that we have this method which is called compute and send credit score, which basically makes a borrow from Aave v3 based on the credit token that we have set in while deploying the smart contract. And then once we have the borrow done, we check whether that this credit token debt is that the dominant debt or not. If not, we revert. Otherwise, we proceed, because the idea is that we want to make sure that out of all the borrowing positions the user has, that this credit token should have the dominant share in that sense. And then once everything is verified, we relay a mint operation, which is basically setting up the credit score on the destination chain. And then we calculate the relayer fee, and that relayer fee is basically send of course like locked in the smart contract. And then we also calculate the CCIP fee, which is paid in the credit token. In this whole example, I've assumed that the credit token is Go, which is the Aave stablecoin launched by Aave, and the source chain is Arbitrum, and of course the destination chain, like I mentioned, is Bob L2. And now, as we see, the trade score has been like the cross-chain message has been sent, and we emit a event. And then we have this slash user function where the relayers can monitor the credit score of a user, and then they check whether the credit token debt, whether it is below the minimum threshold that we have defined here, which is in BPS. And if that's the case, then we compute this slash message and send it again across the chain. And here we also see that the relayer fee that was locked in when the credit score was computed is also being sent to the relayer as well, because now we have identified that this operation is successful. And we again compute the CCIP fee as well, and then we again send the cross-chain message. And the last function is the withdraw debt, where the user can withdraw their locked-in credit token debt, but only after a certain delay, like I mentioned. And based on that, they get back their fee, the borrowed amount that they're locked in, that was locked in this contract, minus the CCIP fee. And then this operation again makes the seizes the voting rights on the destination chain, like the slash operation. So now we come to the credit receiver contract, which is basically receiving the message from receiving the CCIP message. And again, it's very important to have these checks where we are ensuring that we are only accepting messages from a certain chain, from Arbitrum in this case, and also that the sender can only be the credit evaluator. So it's important to check have these checks when you're building cross-chain smart contracts. And now here. This is the function that gets called by the CCIP contracts on the destination chain. And now we are receiving the message and we are decoding it. And from there, we are checking which type of operation that needs to be performed. If it's a mint, then basically what we do is that we set up the credit score for the user, increment, like set it or update it. or otherwise if it's either a withdrawal or a slash, then we make it as 0 and we emit an event accordingly. And then we have this simple yeah, I'll also come to this one, which is the Bob governor contract, which is basically just a simple Open Zeppelin based governor contract, which is used to check whether to trade proposals and vote and execute and things like that. But it is checking whether the user wait, for example, for proposals. There is a certain proposal creation threshold, so the credit score needs to be either equal or more than this in order to create proposals. And for casting voting as well, the voting weight is basically the credit score that was assigned to you, so it has to be non-zero in order to for you to vote on any proposal. So that's the whole uh, uh, the whole end-to-end flow. There's more documentation and more comments in the next part of these different contracts, and then of course there's the readme. And then I'll jump in to the tests, where we have the EIP 7702 delegated tests, which can be again run by the command that I mentioned. Since I had limited time, so I wasn't able to build the UI in time. So the idea is that you can run the tests and do all of these checks accordingly, ensure that everything's working fine. These are like fuzz tests as well, so we take in fuzz inputs, for example, for the batch operation calls, and then we made sure, of course, that that we have the account code being attached to uh, the EOA in this case, and then also making sure that the operations have been executed in the successful scenarios in that sense, for you either using a signature or just directly executing the operations. And lastly, we have these credit evaluator tests, which are four tests. Again, these are like real values on for Arbitrum and Bob L2, in a sense of the CCIP contracts, and then the other contracts are on the source chain, which are defined here. All the addresses, all the parameters, in terms of like configuration and things like that, are being defined, and then we switch defaults multiple times, like here, to deploy contracts on both the Bob L2, the Bob network and the Arbitrum network in the setup function. And after that, we have these different tests where uh, we check for the negative scenarios, and also check for the successful computing grade scores, and making and other credit evaluator functions, testing other functions as well. So it's making sure to do all of that. There were some issues that I faced with the CCIP network configurations with the Bob network, in a sense that the destination CCIP message was reverting with some weird CCIP related errors, which I've noted down here. So with the limited time I was debugging, I ran out of time in order to fix these issues. I also tried sort of debugging it through the documentation, but I ran into some trouble. But these tests mainly contain the source chain related stuff and verification around that. So that works fine. I was following a Foundry guide that the Chainlink CCIP, the Chainlink team has related to CCIP. So yeah, that's all about it. There are tests, first tests, complete documentation, again security checks and things like that. We also have a optimized version, a transient storage version of the reentering guard to ensure more optimization in that sense. And then yeah, that's all about it. We have the whole architecture flow as well here being explained. So I had a lot of fun coding this out and adding these different types of configurations. And thank you again for having all of us hackers participate.